Did anybody message Raphael? He was in the morning class.
All right. So, what am I going to get into today? Well, today we're going to talk a little bit about processes and threads because there's some terminology that you hear all the time, and we're going to make sure that we're clear on what that is. But also because a lot of what we do is building applications that run in our computer, and how they run and when you can take advantage of those multiple processors is key to understanding how your game is going to run more performantly. So we're going to start talking about processes and threads, and we're going to get into what exactly are they and how do they differ. The easiest way to think about it is to start talking about a process. And a process is simply an application that's running. A program that we write is sitting on our hard drive, and that program, once compiled and built, is a set of instructions just waiting to happen. When you execute it, we change its name. It becomes a process. And every process in your computer gets its own chunk of memory. It gets a chunk of memory to put the actual code that's executing in, and a chunk of memory to put that data in. And the data are all the variables you create and all the things that get pushed onto the stack as you call subroutines or functions and get responses back to them. So you can think about the process that's running on your computer as an application while it's live or while it's running. And that program has the instructions being hit at by the instruction pointer. And that data space, as we've talked about before, has a heap which grows from where your code is down towards the bottom of the data, and the stack which grows up from the bottom of the data towards each other. Now, hopefully they don't run into each other, because typically what our operating system does is nothing. It just lets them collide, which means it's possible for one to overwrite the other. When we're building our program, that's when we have to tell it what to do when it starts running out of space. And one difference with game software, particularly in a console, that is different from everyday PC software, is that the act of allocating data space or memory as you need it in an application is actually one of the slower things you can do. So what games typically do is allocate all their memory up front. While the program's initializing, while there's some screen in front of you saying loading, they typically allocate all the space they're ever going to need. And from that point on, that data space is attached to that process and it stays with it. That's part of what gets our program running faster. Now, there's lots of generic terms to talk about the applications we build or the programs we build. And it wasn't really until Steve Jobs came along that he started talking about everything as an app. Up until that point, we had lots of synonyms for the different kinds of programs we have running. We have applications, which we kind of think of as the tools that users use on your computer. Program is kind of a generic term. The operating system is just a program, but it's a program that lets us run other programs. Scripts and shells and batch files we got into the other day. And we threw some stuff at you that let you know that anything that you could type on the command line, you could probably put as a sequence of steps. I mean, those are useful tools when we want to do one-off things, but they're relatively complicated. Or we have some relatively simple set of 2 or 3 steps, and we want to do them repeatedly. We want to do the same steps at the same time every day, and we want to do them unattended. There's a couple other kinds of programs that we write. We talked about compilers. These are programs that build programs. And compilers are fairly complex pieces of software, but nonetheless, they're just programs. Some human being wrote them. Then there's that fancy term in there, daemons and TSRs. And I didn't put TSRs in there, but they're services. Now, services and daemons are the same thing. Daemons, a Unix term for a program that runs in the background and waits to be interrupted by some sort of hardware interrupt. So the operating system loads all these daemons into its memory, and they sit there idle. They're like handlers that handle an interrupt, like a keyboard or a mouse or a drawing tablet or a webcam. All of these things manage the system resources. Probably the one that's running all the time on your computer is the network. The network daemon in the background literally sits there and waits until there's new network packets of data arriving on the network interface or network hardware. And when new packets arrive, that hardware interrupts the processor. And what does it do then? Well, the internet daemon takes over and deals with that data. Now, daemon's the Unix term for it. In Windows, they're called services. And if you look at your task manager, you will be able to find Windows services, and you can look at and list them there. Let's see if we go here. We can go to the Start menu and Settings. We'll get our settings screen. And this is the typical Windows 10 settings screen. Okay. But if we want to get to the control panel, we can right-click on the Start menu and we get directly into the Computer Management panel, which looks kind of like this. Now the fonts are a little small to see on here, and it doesn't really matter what the text are. You can bring this up on your own computer. But inside this are some things that can help you understand what's going on in your computer. The first one to look at is the device manager. And what you see with the list of devices on your computer is not necessarily the physical hardware, but it's all the device drivers. And they've registered themselves with the computer and said, hey, I'm here, I exist, I handle this. I handle my monitor or my network adapter. In addition to this, we also have services and applications. And if you click on this section and look at services, we'll just click to the standard view. You can see all the services running on your computer. They're just listed in alphabetical order. The long description for them should tell you what they're doing. The way these services work is they're applications that run in the background, and sometimes they get time slices and sometimes they don't. Depends on the kind of application. For the most part, they take care of handling all of the different operating system level things that are going on in your computer. Some of them are listening to device drivers. Some of them are doing things like the task scheduling. And all of these services running on your computer get started at different times. In Windows, the status tells you what its current status is, and the startup type tells you how it gets initiated. Does it start when your computer starts up? Is it automatically started? I have some disabled things here. And then there's some manual starts. That is, they have to be triggered or started by some program or application. All of these guys are running in the background. You can see all of the processes if you go to the Task Manager. All the processes that are currently running on your computer get listed here. And you can sort by clicking on any of the columns here to see which one is taking up the most of what. Right now, you can see my GPU is working. Not really hard, but it's kind of working. Right? You can also see my disk is not being touched at all, and that's a good thing. As much as I have an SSD, going out to the disk is a relatively slow operation. We know that, so if I can run everything in memory, I'm going to run a little bit faster. All of these background processes are the ones that you're not supposed to touch or play with. And for the most part, we don't have to touch them or look at them at all, but there are a lot of them. all of the applications that we run show up in this application list at the top. And it tells you what kind of resources they're consuming. Poor old Chrome there. So this is how we can observe the processes running on our computer. They're just the running programs. Now, not too long ago, I think it was kind of 2008, the first iPhones came out. And when they did, good old Mr. Jobs decided that this terminology was far too complex for the average iPhone user. And so he was going to simplify it. And in typical pseudo-programmer fashion, any three-letter acronym or three-letter word that you can use is much simpler than any longer word that you can use. So he came up with the term app for application, and the phrase kind of stuck. Be aware that these days when people talk about apps, they could be any of those things on the left. They could be any of those kinds of programs. Now, as far as the operating system is concerned, everything gets treated the same way by the operating system while it's running. It consumes RAM, it's taking up space, it's relocatable. That is, the operating system reserves the right to pick it up and move it anytime it wants. And generally speaking, we don't care. That's kind of the idea. We want to be insulated from that. The process that's running could sometimes not be responsive anymore to you. And this happens more for developers than it does for people running a program. But if you find something that's not responsive, what do? That process is still technically running. It's still getting a time slice. It's still consuming memory. But if it starts to become unresponsive, it's probably because of a programming error, which is why it normally hits developers more than it hits average Joe. You're building a program, and in the midst of building it, you make a mistake, and your program stops responding. But the process is still running there. So from time to time, knowing that every running program is a process, you would have the ability to go back to your task manager and grab that running program and end it or kill it. Okay? It's rare, so that's kind of a last resort, but you should know it exists. The other parts that are in these settings here are some things that you may see I would recommend against messing around with. Particularly, you can adjust how much gets shown in this chart, but with any given process, I can take source tree here and I can turn around and start up the debugger if you have Visual Studio Community installed. So you can have the debugger attached to that process. If you have the source code, you can point the debugger at the source code at the same time, and they should link up together. You can also play with the properties for that program. And when you play with the properties for that program, there's a few things that you can adjust in here. One of the things that you can adjust with the processes is what priority they run at. And I encourage you to not play around with that too much. The operating system is doing, everyone gets an equal amount of time to play. If you adjust the priority of a process, you're saying it gets more time. It gets more of the application or of the resources of the computer. And the problem, if you start messing with them too much, is that you could create a program, bump its priority to the point where the operating system doesn't have enough priority to interrupt it again, and so you can't stop it. And the only solution to that is to reboot your computer. So while it's possible to change the priorities, try and avoid trying to mess with this stuff. The biggest reason I show you this stuff is because sooner or later you're going to do something that either your program or Visual Studio is going to lock up and not do anything. It's going to die. And when they die, your whole computer doesn't need to be rebooted. What you need to do is bring up the task manager, see if either the CPU is pegged or your application is just unresponsive. It'll give you a note here off to the side when it's unresponsive in the task manager. When we're building applications, all of our applications get moved in and out of memory as they take their time slice. If they all fit in memory, of course, we don't have to move them around too much. And the operating system manages that by managing what we call a state machine. And that's going to be the first thing we're going to start diving into, because state machines are one of these super useful kind of diagrams that we will use to help us define lots of things as they work in our games. And state machines are relatively simple diagrams to tell us a state something might be in and what actions move it to another state. Now, the trick is that in any state, all of the possible actions are listed as arrows going out of that state. And that nowhere in this state machine do you get to a place where you can't get out of. There are no dead ends. Now, this particular state machine is kind of what your operating system is doing with every application as it starts up. Your program starts, we create a process which allocates memory in the operating system's list of running processes. And in that process, we run our application by loading the code, loading the data, starting execution, and putting it into the running state. Now, once it's in the running state, it stays there until the operating system preempts it. And when the operating system preempts it, it stops it from running and says, wait, you've had your turn. And it pushes it to the ready state. And once it pushes it to the ready state, the operating system goes and finds the next process in the list and moves it from the ready state to the running state. And in this way, it keeps everything running all the time. Now, occasionally, that running program does something. Let's say it makes a request to the internet. Well, the instant response to that might look really fast to you, but it's not instant to the computer. So if your program makes a request to the internet, it has to wait for a response. It gets what we call blocked. And when it gets blocked, we turn around and we suspend the process, and then we let the operating system take another process and make it run. How does it get unblocked? Well, quite often it's an interrupter or device driver that turns around and receives some information or some interrupt, and that interrupt triggers some data to be put in some cache or storage, and that in turn triggers our blocked application to become unblocked. And that suspension, once it gets unblocked, we can go back into the ready state. Once we're back in the ready state, then the operating system can pick us up again and let us have a time slice. And now, of course, when we run, there's data available because we've requested it. At a really low level, if you're writing operating system software, this is what you get to do all day, every day. 365 days a year. So it's really, really detail-oriented in that case. And knowing how these kind of state machines work really help you work out what the process is, what your software needs to do ahead of time. The task switch or context switch, when we go from ready to running and running back to ready, that preemptive thing can be a very, very quick operation, or it can be a very slow operation. The thing that determines whether it's quick or it's slow is really, do you have to move things in and out of memory? As the operating system, if you have enough RAM physically on your machine, you can simply change where the instruction pointer is pointing to do what we call a context switch. If you don't have enough physical memory, what the operating system has to do is take the current process, take that entire data and code space, find a spot for it on the hard drive and write it there. Then find the next program off the hard drive, pull it off the hard drive, write it into the space available, reset the instruction pointer, and let that program run. This is why having a machine with 8 gigs of RAM can often be quite a bit slower than a machine with 32 or 64 gigs of RAM. This is why adding RAM to your machine is the single best thing you can do to make it run faster, is because you're removing these context switches. Now, what gets really challenging is what happens if your hard drive gets full. Has anyone ever filled a hard drive almost to capacity?
Oh yeah, I have.
Yeah, and what happens? It gets slow, almost to the point of stopping, right? Now, the challenge here is that what happens when there's no space on that hard drive to write that stuff that's in RAM? It has to do it in little itty-bitty pieces. The operating system is smart enough to try and pull things in little bits at a time. But now instead of doing one operation to pull a big chunk of memory off your hard drive and put it in RAM, it has to pull in little bits at a time, execute a few instructions. Oh, I need some data. Let me pull something out of RAM. Let me pull something off the disk. This idea is that once you get that space filled, both the swap space on your hard drive full, and your memory full, you run into a problem with your computer. The computer tries to keep all of the things it swaps in and out in a file called a page file, or the swap space. If you look at the root of your C drive and you turn on hidden files, you should see a file there called pagefile.sys. That's the actual swappable space on your hard drive. And the operating system reserves that space up front. The traditional rule of thumb there is that that should be at least as big as your physical memory. This is referred to as virtual RAM on your computer. And that virtual RAM, the operating system tries to use as if it's RAM, but it's not quite as fast. And the biggest advent in the last couple of years is the proliferation of SSD drives, which run an order of magnitude faster than revolving platters. So if you think about the speed at which things run, your memory is the fastest, an SSD is the second fastest, roughly 10 times slower. A hard drive is another 10 times slower than that. The network's another 1,000 times slower than that. So every time you're working with a program, you should be thinking about, well, where is this going to go? Where is it going to get saved? Is it so big that it's going to land on a hard drive? And if it's so big it's going to land on a hard drive, how slow is that going to make my machine? If we get to that bad place where your page file is filled up and your RAM is filled up and your hard drive starts to fill up so they can't make the page file bigger, your machine starts to spend more time swapping things in and out of memory than it does actually running things. And that's where your computer gets super slow and where the task manager goes off the chart. And that's the place where your operating system breaks down. And the term is known as thrashing, where you're spending more time writing stuff in and out of your hard drive and into memory than you are actually computing anything. So we want to avoid that. Part of that means when you're building your application, you're going to know what state it's in. You're going to be roughly aware of how much memory and space you allocate when you pre-allocate space. In other words, don't start a C++ application and immediately allocate 64 gigs of RAM. Because when you do that, on most computers that don't have 64 gigs of real physical RAM, it's going to carve off part of the hard drive right away. And that's going to have some adverse effects on your program. Now, All of this is managed by your operating system. The only control you have over it as a developer is how much memory you allocate in your program. How you allocate your memory in your program is going to affect it. In other words, big global variables, public variables, adversely affect this. They get allocated up front, they get space reserved up front, and they're continually there. On the other hand, they're faster because once they're there, you can access them anytime you need them, right? As long as you don't get any name clashes going on. As a programmer, typically what we like to do is allocate memory as we need it, which is a very PC-centric thing to do. The only negative side of that is you don't know how much total memory you're going to allocate until you do it. And so what we want to start to get in the practice of is having a rough idea of how much space we're going to use when we start our application. When we start working with the game engines, you'll find that those game engines take a second to load. And what they're doing is they're going through as much of your code as they can understand and pre-allocating space for as much as possible. And then they're running their own memory management system. In other words, they're allocating 2 gigs of RAM, and every time you need to create a local variable, they're not actually going to the operating system and asking for it via a library or the language implementation, but they're actually making a function call into their own software to retrieve a chunk of information from their own memory management system. And most games operate this way, and definitely all real-time embedded systems do. The other thing that these processes do is the operating system manages that inter-process communication. You can have a program talk to another program, and you don't need the internet involved. You just need the 2 programs to be able to talk to each other. We typically do this through one of 2 mechanisms, and the operating system manages this by allocating some space on the side for it. The 2 ways are with file streams and with network connections. File streams are literally opening up a chunk of your hard drive and treating it like a file where you can write information into it. At its lowest level, you write bytes into a file. If you happen to interpret those bytes as text, well, so be it. But you can write anything there. And be absolutely clear that it's way more efficient to build, say, a structure in C# and write that structure all at once into a file than it is to convert that structure into a string and write the string into a file. And you can read and write these things back and forth. When we talk to the network, it gets simulated in the same way that we write to a file. When we write to a file, we open the file and we get some descriptor or some ID to name it. And from that point on, we use the operating system's library of routines to read and write to the file. When we talk to the network, we do pretty much the same thing. We tell the operating system via a library function called, hey, I want to talk to this network. And when we talk to that network, we're going to identify it with an address, just like you would an address on a piece of mail that you send out. When you connect to that address, you're going to have to tell the computer on the other end which program you want to talk to. And we identify that with what we call a port number. So IP address and port number. Those 2 things specify what you're talking to on the remote end. And the way these things get connected, network programming-wise, is through what we call a socket. And it's behaving the same way as a file. Once you connect up 2 programs via a socket, each of them gets a file descriptor, and you read and write to the file descriptor. You just don't close it when you're done. So if I open up a socket connection to my remote server, I give it an IP address and a port number, and it hands me back a file descriptor, and then I can talk to that file descriptor the same way as writing to a local file in my operating system. I send a structure as a pile of bytes. As long as the receiving program knows how to decode that, we're fine. And this is the crux around network communication and how we communicate between multiple programs. There are ways to make this simpler, and there are layers that over the years developers have added to this basic functionality to abstract it and make it easier for developers to work with. Whenever we start talking to these files or the remote network, keep in mind that these are relatively slow devices that we're talking to. We're not talking about microseconds or thousandths of a second, or 10,000ths of a second rather. We're not talking about nanoseconds like your processor is running. We're talking about milliseconds and sometimes seconds. If you're running 100 millisecond ping time to your local game server, you might be thinking you're doing okay. But if you do the math pretty quick, you'd realize that 60 frames per second equates to 16 milliseconds per frame. So a 100 millisecond ping time means you are in no way running in real time, and that 5 frames pass before you get a bunch of information from the internet. And another 5 frames pass before you send a response back. That means the information you send is at least 5 frames behind where the server is. And its computed response, assuming it can compute things almost instantly, is another 5 frames behind that. So anyone playing a battle royale or a shooter wonder, how do they keep everybody up to date when everybody is 5 to 10 frames behind each other in terms of where the information is? So these are things our operating system has to manage for us. Now, it also has to manage some intermediate stuff that we want to have these days. Apparently, we want some security on our network. We don't want our computer to just blindly answer any kind of request from any other computer out there. So that's another layer that we're going to need. A layer of software that does some error checking and some authentication every time you try and communicate. So in order to make this work, both sides kind of need to agree. And sometimes what we'll do is we'll stick a third piece of software in the middle. And these are often referred to as servers. And by server, we mean software in this case, not a physical piece of hardware. This software server tries to buffer all of these requests. Everybody can connect to the server. And once they've connected to the server arbitrates who gets to see what when. We have to be smart about the way we write our application code at that point, because we know we're not going to get information as fast as we have to draw frames on the screen. So we need to do some smart programming to either interpolate or anticipate what's going to happen. Try and move somebody there. Now, let me flip that into the real world. Anyone played a shooter game recently?
I did right before this class.
Okay. If you've ever played one, and you've probably experienced this at some point, imagine the scenario: you're on your computer, you're behind a wall, you're running down an alleyway, you see the corner ahead of you, you stop before the corner, you go to peek around the corner, and you get shot and killed while you think you're still behind cover. Right? And the answer is, what's going on there? And the reality of what happens is, as you send a packet of information to the server tries to predict where you're going to be 5 frames from now. And when it predicts where you're going to be, you might be, in the open, in the clear, on the server. So you stop before you hit the corner. The server thinks you're in the middle of the alleyway. The server broadcasts that to everybody else playing the game. Their local versions of the game draw you at the center of the alleyway. Everybody opens up on you, you die. The server says, well, 6 people hit you, you obviously died. On your machine, you're still behind the wall. And you haven't been told yet because of that delay. The moment you step forward, you die, and then you rage quit because, how the hell did they hit me? Okay. Now, the better the game, the more time and effort they put into trying to make A, the prediction software smart, B, try not to predict too many frames in advance, C, send information back and forth from the client to the server as fast as possible, and the minimal amount of information you can get away with so that you can make it faster. But ultimately, you're fighting this time lag or this time delay. This is why when you're playing on a longer ping time, you will have a much harder time. The server is measuring your ping time and using that to determine how many frames in advance it has to predict where you're going to be. And they figure out who is correct by the preponderance of the evidence. In other words, if 4 people say you're in a certain spot and you say you're in a different spot, clearly you're cheating. So the 4 people win, right? That's kind of the easiest way to think about it. Now, because of this, what we run into is while our programs are running as processes on our computer, we don't want them sitting and blocked all the time. You can imagine sending that packet off to the server. You still want, as a player, to keep playing. You still want your local computer to keep a nice, smooth 60 frames a second. So how do we do that? Right? Well, we do that with this thing, with processes and threads. Now, what that really means is we're going to allow our main process to keep running, and we're going to make a second process to handle the communication to the server. Now, the reason we want our main processes working is because they're the thing that's handling the graphics and the updates on the screen locally, and we want that to run as fast as possible. But whenever we're going to do a long operation, we want to basically start up another program that's another process to do that long operation. And how do we do that? Each different operating system has a different mechanism for doing it. The term for them is a thread. And threads are lightweight processes forked out of the existing process. In Unix systems, it's done very differently than on Windows systems. In Windows systems, you can create a thread or a separate set of instructions that are executed as if they were their own process. And there's some kind of cool stuff that comes with it, and there's some negative things that you got to watch out for as well. The cool stuff that comes with it is you can identify memory that is shared between your main process and your thread. And this is kind of important because your thread probably needs some information to decide what to do, when to do it, how to respond when it's done. If you're building these in Unity, you will get into building what we call coroutines, which are threads. Yeah. So coroutine is a thread. It's another term for the same thing. If you're using Visual Studio, like Visual Studio Community, and you go into the .NET libraries, you can create a separate thread of execution. The only rules around it is anything that's drawing stuff on the screen can't be in a thread. Now, each thread gets its own process. It can handle responses, it can listen to IP addresses and port numbers, it can start its own communications, it can start up and shut down multiple times while your main process is running. It's expensive to start up and shut down, so we want to keep that to a minimum. And with shared memory, we also have a little bit of a problem in that sometimes, if we're both trying to read and write to that memory at the same time, we can run into much more serious problems. Now, it's also important to recognize that if you're on a computer that has only one CPU, multiple threads do nothing for you because they just take up another time slice. Where multiple threads help you, especially when we're doing game software, is on our modern CPUs where we have multiple cores. Because the operating system will take your thread and run it on a separate core. So it actually will do some parallel processing. Because those threads have access to some of the data in your main process and all of the file handles and sockets in the main process, it's up to you as the programmer to write what we call thread-safe code. And thread-safe code has a bunch of properties that, we're not going to get into all of them here. But some of those properties are the fact that you can't be writing into shared memory if someone else is trying to read from it. You can't be writing to a file while someone else is using that file. You can't be writing to the internet while someone else is using it. And you need to come up with things in your software to prevent those bad things from happening. And all you have to do is kind of imagine what happens if the thread is waiting for information coming from, say, the network connection at the same time that your main process is writing to the network connection. One of them is either going to be unable to write or unable to read, and they're going to either wait forever or get blocked. So the operating system blocks the thing writing and waits forever for the reading until the blocked thing that's trying to write can finish. But the blocked thing that's trying to write can't finish because it hasn't finished reading yet. And it stays like that pretty much forever. So we have to build software that makes sure that that doesn't happen. That doesn't come for free. That doesn't come out of your operating system. Yep. Where can we use this in games? What kind of stuff? I've already talked about networking. What kind of areas in games do you think you would use a separate thread to make things run a little faster? Yeah, definitely. Anything that you want to run on a timer, you could put timers into coroutines or threads. What other kinds of things?
You guess any expensive tasks like maybe AI?
Yes. Yeah, any expensive task. So AI is a classic one. Any kind of pathfinding, routing, which thing is going where, when, which thing has priority. A lot of times when we're doing this stuff, we don't have the time to do it at 60 frames a second, but we also don't need it at 60 frames a second. If I have 10 enemies on screen, all I really need is a vector for where they're headed, and they can continue along that heading until they get a new one. So if it's a long computation to figure out where the next heading vector is, I can fork that off onto a separate thread, compute it on the side. When it's ready, I just update their heading vector. Right. Think about things like physics. Right. Physics is a fairly complex mathematical operation. Particularly, we're going to do a bunch of it when we start talking about rigid bodies. And as we start doing a bunch of rigid body math, we're going to have to do some long mathematical computation. We're going to try and find a way to make that happen relatively quick. How about user interfaces? Right? Now, the drawing on the screen is one thing, but keep in mind that what happens on the keyboard and the mouse and the game controller, not necessarily one-to-one linked with 60 frames a second. So it's highly likely that you want to take all of the inputs from the keyboard and process them separately. almost peeling off the important ones and putting them in a queue for the main game to act on, meanwhile accepting more inputs. And you probably also want to do something that debounces things. And different game engines have different ways to do this built in, but if someone comes along and leans on the W key and you get 6,000 W key presses interrupting you all at once, do you need to deal with 6,000 or should you just start the person going forward? Like, you don't need to change that until they hit a different key. So debouncing is a matter of taking those inputs and squishing them down into, okay, yeah, but you're leaning on the W key because you want to go forward. I got it. Moving on. Yes, if you hit the W key a billion times, I'm just going to ignore them until I get something different. All of these things are kind of the cool things that we would think about putting into separate routines. It's important also to recognize that debugging these separate routines is challenging. Particularly, you're now dealing with timing. When does this coroutine or when does this thread start and end? And that organization and optimization really triggers a bunch of potential problems that you're going to run into. Specifically, you get too many threads running, and the threads either can get stuck waiting for another thread, or you can't do the main big thing until the small thing is done. And all of that extra waiting time is just slowing you down. So the theory behind using multiple threads is really one of, it's something you use sparingly as a developer, generally speaking, while optimizing your application, and or if you have something is going to be really, really slow and long, you can from the outset plan on it being in a separate thread. Typically, the most common ones: physics, network operations, sometimes inputs. And the different game engines that we use do this automatically for you. So when you're working within Unity and Unreal, they'll take care of this part for you. When you're building your own game, your own engine, and you need to do some of these things, you have to think about, do I need to take care of this myself? Some of the downsides of doing multiple processes and multiple threads: first off, obvious complexity. And that's where we're going to get into starting to do some diagram stuff. If you work out the complexity ahead of time with some diagrams, you will have a much easier time trying to implement. Timing and synchronization can be a problem. If one thing's ready or waiting for something before another is ready, that becomes a problem. Not every platform and every environment we work in supports multi-threading. So the heads up is JavaScript doesn't. Python doesn't. Right? C# does, C++ does. So different strengths and weaknesses there. It takes more work. That's that planning notion. And that's what we're going to dive into a little bit. I'm using this as an intro to this. What I really want to get to is some of the state machine stuff, because the state machines are the way we plan out some of these multi-threaded timing issues. But before we get into doing those timing issues, we're going to do some state machines on much simpler things, because state machines are a great tool for you working out how something might work or how something might operate. And they're used all the time in games. What people refer to as game AI, 99% of the time has nothing to do with AI and machine learning, but it's just a state machine or a decision tree. We got to deal with deadlock problems, which is what you see with the little bus example here, the little text you can't read. What if two people try and book the remaining 2 seats at the same time? Right? And in the example they have here, the bus has 3 seats and both parties are trying to book 2. So who wins? And the answer is nobody wins. This creates a deadlock problem where each person trying to book seats gets told that they can book the seats, but the actual booking can't happen because there aren't enough seats to go around. And so they're both waiting and requesting at the same time. We do get a little bit into that non-thread safe stuff. What thread safe code really means is that the only variables and information we want to use are very specific ones that we use some special software techniques to protect against deadlock. Other than that, every thread should do as many things in its own private memory space as possible. In other words, declare its own variables and use them locally. And that means that we only use those shared bits of memory as a communications device, and we have to wrap them in some software to make sure that only one person can write them at a time. So, how does this all fit together? Well, like most things, we want to design before we just sit down and code. And the more complex things we build, the more this is important. We sit down ahead of time. And one of the best tools for doing this is a state machine, because a state machine lets us know what part or what agent or what entity in our software is in what state at any given time, and what events change that state. The most common examples that people use typically involve things like vending machines, game animations, AI states, language parsers, and compilers. And the vending machine is probably the most classic example that people use in universities to try and teach state machines. If you think about state machines, what we're really trying to show here is what are the different states this thing can be in. So we're going to start by thinking about things. So if we look at the vending machine and we just kind of walk our way through it, a vending machine has a bunch of different states. The first one is it's waiting. It's waiting for coins, right? When it gets coins, it goes into another state. It starts to compute how much money's been added. And it doesn't switch state until enough money's been added for the minimum price thing in the vending machine. Once it's got to that minimum price thing, two things can happen now. Either you can add more money, or you can make a selection. So as you talk through it, we start to think about, well, how would we diagram that? States go in bubbles. The transitions are arrows between the bubbles. Straightforward. Keep it simple before you start looking at tools. Now, there are tons of tools out there, and I'm talking about drawing tools like Visio and Miro and Google Drawings are all tools that have templates and styles of documents that will do like these formal software engineering documents. But I recommend you do them simple to start with, okay? So start thinking about one of the things we're going to do. I'm going to take a good break here. And what I want you to do when you're coming back from that break is to start thinking about how would we build a gas pump, like at a gas station? What states would it be in? And what are the things that change or transition its state? Okay, and we're going to diagram it with just some bubbles and some arrows. Okay, just as an exercise to get our heads around doing some state machines. Yeah, we're going to do this one together. Okay, but what I want you to do is think about what are all the states that gas pump could be in. Now, I'll come back at probably 10 after. Okay, and we'll kind of scribble this down. I'll write it on my little tablet as we go.
Just one thing. I was late because the bootbar had an API outage and my computer wasn't updating. So I checked my phone and I saw that because I started about 2 was just late. Sorry for that.
Right. No worries. You can always check discorddatus.com and get its current state. Right. So we talked about building a gas station pump. Right? So when we pull up to a gas station pump, what kind of things did you come up with that we would actually use? But what's the first state it's in?
It's waiting for a car. Well,
It's waiting for a car, yes, right?
Come on. Let's go toys. Let's make that a little smaller, maybe. Come on. That's one state. What other states can it be in?
Pumping.
Pumping. What other states?
Selecting fuel type, just gasoline or
Yeah, like what octane you want or whatever.
Right. What other things do we need?
It could be processing pay.
Anything else?
be like as a service maybe.
Let's not deal with the errors so much.
Okay.
All I'm thinking of is like when the tank's full. Right? So then we can start figuring out the transitions. Like I said, tank is full. It goes from pumping to shut off. So from waiting goes to authorizing, right? And you can even do links to yourself. But states are places they sit until some action gets them out of that state. So approved now, if you want to deal with the simple kind of error states, failed credit would go back to waiting, right? And from selection, my C is really bad there. Octane. And once it shuts off, what does it go back? It goes back to waiting. So straight away, this is kind of a state machine. This is exactly what we're looking for. And the part about doing these things is that it helps you solidify in your own brain how this might work. before you go code anything. It also gives you the ability to sit down with another developer, regardless of their background, and go, hey, if you can follow this, it probably makes sense. And what did I miss? What can happen while I'm waiting that I haven't got here? Well, while I'm waiting, I'm either going to authorize some credit card or what else? I can't go right to pumping. I can't go right to selecting fuel. Right? I could add some error states if you pick up the nozzle too quickly before you're authorized. And I could create an error state if I wanted to for that. And the whole point of doing these diagrams is to facilitate a discussion between you and the other developers on the team to see exactly how you're going to implement something. Now, when we do this with software, what we're really going to end up thinking about is how do we use all of the shared resources we have available to us, and do we need to diagram how we're going to use them? So if we think about, a save game, or one of the first tasks that most junior developers get as they're building games is do the save load operations. Could you sit down and in the next, say, 10 minutes, diagram on paper for yourself? I'm not going to ask you to hand it to me, but can you diagram what a save load would look like for a PC game to make it easy, right? So the user hits pause and then save game. So from the moment they hit save game, what kind of state diagram do you have for what are the good and bad things that can happen? You got to take care of what happens if I don't have enough space to save that game? What happens if I choose a file name that's already been used? So I'll give you like 10 minutes to try and work that out. I'll leave you with this diagram so you get the idea of how we draw these things. Maybe another couple minutes to play with this. Just get comfortable grabbing a piece of paper beside you when you run into one of those complex problems. Go, like, how does this work? And if you can work it out in a diagram, you don't even have to write a big long document. You don't have to write something that has a whole bunch of text around it. You can do a diagram and pull some annotations out on it. Now, this is one of the tools we use. At this point, we're going to dive into some of the other tools we can use. When I leave you with the slides, there's some additional stuff in there. You can actually use a state diagram when you're dealing with multiple threads to help you visualize how you would keep your multiple threads from running into each other, from deadlocking each other. You can just draw in kind of the different states that each thread would be in and when they're reading and writing some data. And the general technique for doing it, before we get into too much detail, is by using some simple flags, where that every time you want to write some data, you go check to see if there's a flag set that somebody's currently using it. And if the flag's set, you wait. And you check the flag again and again and again and again. And a separate thread can set the flag, change the value, and then clear the flag when it's finished writing that new value. Then the other thread that's waiting will see that the flag gets cleared and go, oh, flag's cleared, someone else isn't using that right now, now I can go use it. And you can use a state diagram to see this. The other two places you're going to see state diagrams, absolutely for sure, when you're developing any sort of autonomous behavior for any entity in your game, particularly enemies. And I know the propensity is to call the enemies AIs, but AI is, one, the wrong term, and two, we use all sorts of different methods, not just related to enemies. But it's worthwhile doing one of these state diagrams for any kind of enemies you build into any game you build. However simple, the diagrams can start out simple. Quite often people get into problems where they're like, I've got an enemy and, he's patrolling, but he doesn't know when to go search or when to go into a certain, looking for the player or something. And you're like, well, that's a state diagram. So what states can your enemy be in? Patrolling, searching, attacking, retreating, whatever. And then what are the things that trigger those state changes? And that one's very much a loop, you know. And you can make one of the conditions kind of like a line of sight test. I am patrolling. When I have a line of sight with the player, I go into attack mode, into the attack state. They don't have to be a complete loop. You can make shortcuts across different states. You just need to have an idea of, I'm in this state, this thing happened, I go to that state. And when we start implementing software behind it, there are relatively simple software constructs that let us keep track of these things. As we start looking at your whole application, we start realizing that there's probably other tools and diagramming techniques that can help us when we start looking at whole applications. In particular, games sometimes can be relatively complex. We have a lot of different moving parts. And what we want to emphasize here is, as far as moving parts goes, the way you deal with large complex systems is you break them down into smaller systems that are less complex. And then you take a look at the smaller system and you break that down into a smaller system that's less complex. And you continue to do that until you get down to something that is small enough that you can understand it. At some level, you're going to have some picture of the system you're building. And so we're going to dive into how do we do that, okay? And there's a very specific methodology for how we approach this. It's a methodology that has been developed over many years and had lots of software engineering professionals kind of contribute to it. And it's been kind of unified into a single methodology. And the beauty of this is that once you get used to this methodology and you recognize that every other software engineer on the planet kind of gets trained the same methodology, you can sit down and work with somebody you've never worked with before and immediately dive into your problem and be able to talk the same language. And the key here is just having a place you can diagram things in the same notation and the same language. So where do you start? Well, this unified approach that I'm talking about is pretty generic across all engineering problems. It always starts with understand the problem you're solving. And far too often, particularly when we start building software, we get really excited and we're learning new languages and we're learning new constructs. And the first thing we do is we jump in an editor and we start writing code, right? Which is generally the code we're going to throw away 3 hours from now. Because as we start to do that, we inevitably learn more about the problem. And as we learn more about the problem, we realize that the code that we wrote had nothing to do with the problem. Or worse, we start writing some software to solve a problem that isn't the problem we really have because we don't completely understand it. So the hardest part is to completely understand the problem. And when we're building games, I think I've said this before, the biggest thing we're trying to do with games, the problem we're trying to solve is how do I get an emotional reaction out of a person? How do I trigger that emotional reaction? And there's a bunch of different techniques to do this. But understanding that that's our goal will help us ultimately when we realize that when we're trying to get that reaction, that means something has to happen that the user has to interact with. Something happens they have to deal with. Now, how do we kind of wrap our heads around that? Well, I think the other part is recognizing that games are simulations. And simulations have things in them, right? And we have to somehow quantify all the things and all of the things that those things can do, or all the actions that those things can take. And we put those down in what we call requirements, or use cases is the term. As a player, I can press forward on the controller. Now, use cases have a very formal definition in this unified approach, in that they typically have some very specific English language construct around them if you're doing them formally. They're typically listed in some sort of spreadsheet. And depending on the rigor in which you want to go into the software engineering side of things, you're going to diagram every one of them. You're also going to set up a use case for every different thing in this simulation that you're working on. And so we have some terminology that we use with that. The things that we're interacting with are typically called actors. And you can see how this starts to relate to games. But the actors could be a system to manage magic points. As long as there's some entity that we can talk to, some entity that we can wrap behaviors around. Normally, we're going to try and relate them to real-world things, or pseudo-real-world things. Characters, enemies, environment, that kind of stuff. And our use cases are going to be all about what are the things these entities or actors can do. And the real trick when you're doing these use cases is that when you write them down, you don't ever use the word and or. In other words, if you were going to use the enemy can attack me and do damage, that's two separate use cases. And you write them separately. Now, I bring this up as kind of the process because what you will observe is that very few people actually observe every step of the process and write them down. As you're learning the process, you'll often see, especially the worst for this, are instructors. Because we'll skip steps to go quick, because we've done this problem before. And we'll skip a step, and you'll be like, well, I don't understand how you got from there to there. Okay, so recognize that if you don't understand how you got from one place to the other, to stop somebody and say, hey, I don't get how you got from A to B. Because we're going through this process in our head. Now we'll try and diagram and write it down. So I know the problem. I've got some use cases. And in those use cases, I'm going to write all about the actors and what they can do. As a player, I can move around the game. As a player, I can cast spells. As a player, I can shoot arrows. As a player, I can pick up items. Those are all nice, valid use cases. Okay? From those use cases, if you take a job as a requirements analyst, what you do is you talk to people about their problem and their system, and you write use cases. From the use cases, if you're doing it formally, quite often what we do is print them out and grab a couple highlighters. We grab a pink highlighter and a yellow highlighter. Pink highlighter for nouns. What are nouns? People, places, and things. What are yellow highlighter is for actions. What are actions? Verbs, action words. Okay. And we go through every use case and we highlight the noun and the verb. Why do we do that? Well, because we're going to create a model of our simulation by building a class diagram. And the things that we're going to turn into objects or classes of objects are nouns, because objects are things and nouns are things. So you walk through all your use cases and you grab all the things that are pink highlighted and you make an object for each one of them. Okay, that's nice, Scott, but now I just have a list of stuff. I got actors, I got objects. Well, we're going to diagram these objects with a very, very complex symbol. It's called a box. And everybody can draw a box. And we're going to add to that. We're going to augment it with a few symbols as we go. Okay? We're going to take that class diagram and we're going to identify the relationships between the different things. In other words, if I have a player as an actor, I'm going to have a player class in my class diagram. That's probably something that's highlighted as a thing. And if that player also has related to it an inventory of items, the inventory is another thing. And that inventory has items. Those are other things. But what I need to identify is that the player has an inventory, and the inventory has items. Because those things I can turn directly into software. Once we have that class diagram, that's a best guess at the entities or the things we need to build in our software simulation. And we probably need to test it to make sure it works. Again, we do all of this on paper. And this is one of the places where being physically together helps, because quite often when teams do this for real, they focus on the most important use cases, not every single use case they listed. And they focus on, hey, how's this going to work when I cast a spell? And one of the ways we do that is we doodle that class diagram on a whiteboard, and then we go test it. We walk through it verbally, and we diagram that with something that in this unified approach is called a timing diagram. We show how the actions affect each of the things over time. Now, there's a couple other diagrams that come into play that can help us along the way, but I'm going to show you class diagrams, I'm going to show you the relationships, and I'm going to show you the timing diagrams, and then I'm going to get you to do them. I'm going to get you to do the diagrams as a picture that you can hand in as an assignment, because this should be a relatively straightforward assignment. The stuff I'll get you to build in the assignment is going to be missing pieces, and that's okay. You're just going to diagram the subset or the pieces you know about. But we'll do a couple samples first, okay? This unified approach is literally called the Unified Modeling Language. It was first developed by a guy named Grady Booch, who is a professor of computer science, and in consultation with a lot of other professors who poked holes in his unified modeling language, he eventually came up with an entire suite of diagrams. There's about 30 in all, that can completely diagram any kind of software system. And there are tools you should be aware of that are out there that if you can go into the tool and diagram a class diagram, list actions, list actors, and build timing diagrams, you can, with the push of a button, generate code. You draw the diagram tool generates the code. Now, the code doesn't generally have a lot of guts to it, but it is framework. So if you decide that your system is complex and has 30 different classes of objects in it, with a push of a button, you can generate those 30 class files right off the bat with all the right syntax and all the right stuff in it. And then you can start to develop. Okay, so those are time-saving tools for large autonomous systems. The only piece I'm missing here really has to do with data. And sometimes our entities or objects have a ton of data attached with them. And we want to know how the data is related, which may not be exactly one-to-one with the classes or objects that we create. And those things we can diagram in what we call an ERD, or an entity relationship diagram. Now, these aren't used all the time anymore. If you have a decent class diagram that has all of your data attributes in it, they're redundant. You don't really need them. But if you're doing stuff that's storing information in an offline data store somewhere, you may want to learn how to build these. Of course, there's the state diagrams I've showed you about already. Okay. So, how do we start? Well, we start identifying all the things, the actors. And then we put together, like I said, all the use cases, right? As a whatever, I can fill in the blanks. It's kind of a global statement. And the reason I want you guys to see some of this is that sooner or later you'll run into a problem that is, how do I start? How do I've never seen something like this before. Where do I begin? And the place you always begin is understand your problem, list the actors. What are the entities that are going to be working here? And from the actors, you can start play testing. Literally, as an actor, I can do what? As a player, as a user, sometimes I'll define a user independent of a player. User is who's using the software. The player is the avatar on the screen.
The user can save the game, but the player.
Right, exactly. As an enemy, I can patrol an area. Right? As an enemy, I can attack the player. Hey, can the enemies attack other enemies? No use case for that. As an enemy, if I take too much damage, I can retreat. Again, if is fine, no and, no or.
Just one sentence.
Just one sentence, right? So if you're doing this end to end, every step of the way, essentially what we end up building is a spreadsheet with a list of all the actors and all the use cases, and then a class diagram. And then we'll choose a couple of those use cases to test our class diagram. And we'll test it by using a timing diagram. Don't worry, I will show you what these all look like. And the timing diagram will either work with the class diagram we have or force us to change the class diagram, in which case we found a problem. So let's take a look at how this kind of fits together, this methodology, right? So list all the actors, identify the use cases. Let's show you some of the diagrams to start with. Now, to build a basic class diagram, all we need is a few boxes. And these boxes have some relationships in between them already. The boxes themselves, we generally put some labels on. What you'll find is that as we get lazy, we tend to not fill some parts of the boxes in. So in particular, let's see if my little annotations are there. Oh, yes, they are. All our boxes have a few things in them. The first thing is, in the top of the box, we give it a name. And that name is always singular, and it's always a noun. And it always starts with a capital letter. In the next box down, we can list all the properties or attributes that all the things of this class of being have. So if it's a player and they have strength and dexterity and endurance and intelligence and education as properties, those go in that second box. And if you're being really diligent, you want to have this work through some automated tool, you probably have to specify types and initial values too. And then in the bottom box, we put what we call methods. These are the actions that this entity can have done to it. Right? So if a player can walk, then walk is a method on the player. You can tell the player to walk. And it's literally like sending them a message. Say, do this, do that. And they're always actions. Okay.
How are you supposed to name the class again?
They're nouns. Always singular nouns. Player, not a player. Player, not players, plural, just player. Okay. And then the next part we start to identify are the relationships. And the relationships really, there's lots of different variations on this, but they come into two flavors. The first one has a relationship, and the second one is a relationship. We'll diagram something like the player and the inventory again so you get the idea. Okay. Arrows represent is a relationship. So if I turn off my annotations and I just use this, if I say this is, let's use that one still. So this is A, this is B. Okay. if I decide that, let's do C. Let's decide that I'm going to say C is an A. That's all I have to do. That tells me that if A is a thing, C is a special kind of thing. The other annotation here, the little diamond, says that B or A has a B. So this one A has a B. In this one, B has N C's. Now the thing we're looking at here is what I've really specified is that A is a thing, B is another thing, A has one B, and B has multiple C's or has a list of C's. But at the same time, I've diagrammed it in a way that you as the programmer are not told this is a list, this is a linked list, this is an array. That's up to you. That's an implementation problem.
Yeah, so I think visual example definition was like player has an inventory. And
right.
The inventory has different slots that would be C, for example.
Yeah, that's right. Here, let's just put those together. So, right? A player has an inventory. The inventory has multiple items. But item is singular. This is an item. The relationship specifies how many. And let's just say, for instance, that I have an axe. An axe is an item. Is a, right? Or is an item. Now, the thing I like about doing this, particularly as a diagramming exercise, is once you get used to doing these UML style diagrams, a few things happen. One, every software developer on the planet gets taught UML these days, which means I can sit down with somebody that I've never worked with before, go to a whiteboard, I think the system should work like this. And they can look at that diagram and immediately know what I'm talking about without any ambiguity. And if they think I'm completely wrong, no, the player has a list of items. There's no inventory thing in the middle. Then they can have that discussion with me and we can draw it both ways and see what works. Okay. So that's the notion of doing a class diagram. Now, there's a lot more details to this. And for the most part, you don't need 90% of the details. Sometimes the diamond heads are filled in, sometimes they're not. That's where you're trying to specify whether something's always there or only there when you need it, that kind of detail. But really, boxes, relationships, once you get past this stage and you start talking about, hey, is my health a separate box or is it just a property on the player? And again, you could debate that depending on how you might want to think about the implementation. If it's just a property on the player, you can write it in. Right there. If it's a separate thing, then you can diagram it separately. My player has health. Okay, but your health is just a single number. Is there anything special I can do with my health? And here's where you get into not all software is the same, depends on who makes it. The advantage of having health as a separate thing like this is I can attach my health to any other actor in the game system. And if the health carries with it things like heal and do damage, then I don't have to like write those 3 or 4 times. I can just attach those to anything in my system. On the other hand, it's a really simplistic concept, and to add an integer to the player and a couple methods for taking damage and healing damage doesn't seem like a lot of work. So that's another possible implementation. And how you diagram and how you talk about these things will lead you to, okay, how do I build a bigger system? Well, I just keep building this class diagram larger and larger and larger, adding all of the entities listed in all my use cases. The other beauty of this is that even if you've never seen UML before, with the short little description I gave you about how to read the 2 different arrow types, you can probably teach a game designer this entire diagramming. Which means even if you can't get out of them, hey, how is this supposed to work? Maybe you can sit down with them and work through a diagram of how they think about things. And from that, that conversation will help you answer the questions that you need to be able to implement it. Now, how exactly do we test these out? And that goes into that next step, the timing diagram step. And the timing diagrams, where a class diagram is a global thing. It's kind of the class diagram is the structure of your application. The timing diagram is how does it behave over time. So I'm going to redraw this a little smaller, and we're going to see if we can kind of put that whole timing diagram thing together. So let's turn that and that. So let's say I go here, and I'm going to build that timing diagram, or the class diagram to start with. It's really hard to find software on the internet that lets you do this quickly. So there's my class diagram again. Well, the timing diagram what we're going to do is we're going to start with a specific instance. So here's our player. And in this case, time runs down the page. And what other things do we have? My inventory. Oops. And then potentially an axe. So the way we test this out is we use those action words, those methods. Let's say my player pick up an axe, right? So it's going to send a message to the axe, say, go get yourself, so that the player has a reference to it. And then it's going to tell its inventory, yeah, I'm not doing very well. We're going to add an axe, right? If there's any other information that has to go back and forth, we can list the activities here. Each one of these things is an action. You notice they're verbs, they're action words. And if I ever try and say, hey, well, okay, well, how do I get an axe? Where's the item, right? Oh, well, I had an axe. Which is really a specialized item. And in case you don't recognize it right now, the arrow is inheritance in terms of object-oriented programming, right? And the has-a relationship is aggregation. You have a variable. The player has a variable which is an inventory type. My inventory. Yeah. Hopefully you can see kind of with these simplistic versions of these diagrams how you can completely define the software you're going to build without ever writing any software. And if there's something that's missing, you know, hey, but I also need to do something with the axe. What? I have to, find its encumbrance. Well, everything has an encumbrance. Every item has a weight. So you start adding things. And so you can continue to add these things as you go. And as long as the items or the entities you're creating at the top of the columns have a corresponding class diagram item, your class diagram is good. And at the end of the day, when you want to figure out what methods are in the player, all the methods that talk to the player go in there. All the methods that talk to the inventory go in here. All the methods that talk to an axe go here, and anything that happens to any item goes here. And now you have a diagram. Now you can sit down, I can give you this, and you can go build an axe class for me. You know it's got a constructor, you know what properties it has, you know it inherits from item, and you know what methods it has to have. Get weight. Crazy, right? Software Engineering 101 in less than an hour.
It's cool. If you want to discard X, you have to
Yeah. And if you find you're adding something on the end here that doesn't exist in the class diagram, well, then your class diagram's missing something. So it's time to go back and look at the class diagram again and say, well, wait a minute. If I build it that way, I won't be able to do action Y. I need to be able to do action Y. I need to be able to find a place to put action Y. So now I either need to go back and change my class diagram, or I need to change the way I have these objects talk to each other at runtime. Now, this is a really simple example. Another example that always seems simple would be a good one to practice here. Right? Do the login flow for a game. Think about all the entities you got to deal with. Don't worry about networks or communications. Just assume they're all just things you can talk to. Right? You've got a user. The user has a username and a password. Right? And then you have to have something that authenticates that user. Right? Plus, you probably want to identify at this point the user interface things. I have the login dialog. I have the failed login dialog. I have the add account dialog.
Well, that's a lot of things when you put it that way.
Yeah, but that's why we have these diagramming tools so that when it gets complex, you can diagram it out. Because if you can imagine diving into code and just start writing code, you're going to get so confused with what you're building, it's going to be a mess before you begin. Where spending a little bit of time diagramming out a more complex flow to begin with is going to give you a roadmap or a plan on how to implement. Okay. Take a quick look for yourself. I'll give you like 10 minutes to just kind of play around with some of this on just pen and paper. Again, nothing to hand in. Just look at that login flow and see how many areas are just like, oh my, this is complex, because login is not a simple problem. Yeah. Yeah. All right. I'll come back about 20 after. And then we're going to look at the assignment. All right. Are you convinced that that's a non-trivial problem?
Yeah.
So the good news is, in all the applications we're going to build, I'm not going to ask you to build a login flow for anything. And that's typical in app and software development. We'll make the app work before we start layering in security and logins and user authentication and all that kind of stuff, because it is a non-trivial problem. And people kind of look at it initially and go, oh, that's pretty simple, just a login dialog. And it's like, there's a little bit more to it than that.
One question.
Yep.
Your class type can be 2 words or it needs to be just 1 word?
It should be 1 word. It can be 2 words as long as there's obviously no spaces. It's just on camel case.
Like logging error.
Right. But in that case, what you would probably do is make an error thing and make a specialization called login. Right.
I have a nosebleed, Scott. I will be right back.
All right. Go fix it. Okay. All right. Just as a reminder, this is the full methodology. Okay. Identify the problem, list all the actors, identify the use cases, propose a solution by coming up with a UML class diagram, test it with some timing diagrams. Most military spec type software will require you, if you were to do it, to physically list out every use case, every actor, every class diagram, and do a timing diagram for every single use case. That is kind of the definition of military spec. We build games. We don't do that. Okay? What we typically do is stop at the class diagram. We ask the game designers to do the use cases. I mean, if you're designing the game, you should be able to tell me all the things the player can do, right? So if I give you kind of like a sentence with some blanks, you can make a spreadsheet full of those sentences of all the things the player can do. Oh, we got these enemies too. Cool. Put the enemies on a separate list of use cases the enemies can do. Oh, but we got this giant orb that throws globs of goo at you. Okay, good. The orb has a bunch of use cases too, correct? Oh yeah, and the environment has like these like opening and closing door. Cool. The environment has use cases. Like, you just keep listing them. Okay. If you get every use case, you have a complete design, where at least you have a good chance at it. The UML class diagrams, I think, are super helpful. They help you identify what it is you're building. And they're independent of the graphics and what you see on the scene or the screen. Okay. The testing the things out, those timing diagrams, they're very painful to do anything complex in, but they're also very helpful. So what I recommend is, when you see a use case and you read it and you're like, oh, that's going to be a problem, do the timing diagram for those ones. And it'll be less than 10% of all the use cases you get. Do the timing diagrams for the things that you look at and go, oh, that's going to be a problem. I can see that I'm not sure that's going to work. Or I don't know how we're going to make that happen. All right. Let's start in this. Not this one. Let's do this one. So we're going to start into an application. There's a further description of this that I'll put in Moodle for it. So a lot of this is written down, and it will be in the slides that you have here. We're going to have you do a breakdown for a fictitious game. And this game has a bunch of things in it. Okay? These are the entities. These are the actors in there. We have the game itself. The game can trigger things to happen all on its own. So the game is a living, breathing entity. We have objects in the game. Some of them are flagged as smackable and breakable. And those are highly technical terms that game developers use all the time. I'm pretty sure you get the idea what a breakable is. Right? And a smackable, does that make sense?
Could you explain it? Is it like a? It's like an object. Like a.
It's a thing with physics on it.
Yeah. Okay.
So when you hit it, it tumbles. Right. Right. Whereas the chair might be a breakable. Okay. Plus, in this fictitious game, we have enemies, and we have a mob of enemies, a collection of them. Plus, we have the player, and the camera is a thing, and the world is a thing. All right? What I want you to do is create a class diagram with these things. There's no guarantee that they're all related to each other. So there might be a class diagram, but with no arrows or links connecting one part to the other. Although it's pretty reasonable to assume that the game has a world and a player and enemies and a camera. And that the enemies are in an enemy mob. And the world is full of smackables and breakables. And if you organize them kind of that way, all of a sudden, all of these non-related things kind of feel like they kind of all fit together. And then I want you to try and build a timing diagram based on that class diagram. And in that timing diagram, we're going to put a whole bunch of things at the same time. So we're going to be able to tell the game to update itself and tell the game to run. And when the game runs, a bunch of different things will happen. And this is in no particular order, but the things you can tell a smackable or a breakable are to break themselves, to hit themselves, to run simulation, and to collide with other things. The things you can tell enemies are to go pathfind, to go set a new heading, to accelerate, or to do some action. So we can have generic action.
The new position?
Yep. Yep. There's no guarantee that these things are related to each other. Mm-hmm. You don't have to make sure that the enemy has something that hits a smackable that does a simulation and a collide. Those have no requirement for them to be together. What I'm looking for is the diagramming notation. Okay. So we've got some methods that can be applied to each of our specific actors. And it doesn't matter what those methods are, really, other than you can probably figure out a rough relationship between these things. Okay. It's not about getting the relationship 100% right. It's about getting the diagramming notation 100% correct. To be clear. Okay. Now, diagramming them on paper is fine, and I will totally accept that. Diagram it on paper, take a shot with your phone, make a PDF out of it, put it in. That's cool. If you want to go more and do more, there are tools to help you do that. If you're on one of the school computers, I believe Visio is there, and Visio has software engineering diagrams, and you can look up class diagrams and timing diagrams. They'll look slightly different. I think they look kind of like, I'm skipping around here. Is it that one? Stuff like this. This is the software generated version. You notice the one on the left is kind of just boxes and arrows, and they're using empty arrows instead of the diamonds. The timing diagram is on the right. And you see a little bit more complex, right? When you get the slides, you'll be able to read the text in there. But you'll get the idea of how these things are laid out. Time flows down the page. These things happen and come back. This particular timing diagram has an added complexity in that it lists asynchronous calls. That is, calls that don't have to come back in the same sequence they were made. And those are denoted with dashed lines. And you don't have to worry about it too much for now, other than, wow, that's kind of cool. But I guarantee you in term 2, we're doing asynchronous programming. So it's coming. One of the other things you can do is you can use tools to do it. So if you're at the school computers, Visio works really well for this. They allow you to draw boxes and connect arrows between the boxes, and when you move the boxes, the arrows stay connected. The other online tool we've been using a lot is Miro, which you can sign up for. It's a free tool. And they have a bunch of software engineering charts.
They use this one for brainstorming.
Yeah.
Game jam.
Yeah. If you kind of look at their...
For the name of it, so just don't the bother.
Oh, look at that. UML diagram. So, again, they're boxes with sections and little arrows of the right kind to tell you what's related to what. Okay? So feel free to use that if you want to do a formal version in software to generate your diagram. I recommend you spit out a PDF when you're done. It's just easier to share things around. Okay. Now, as you create that timing diagram, right, you're going to list all the entities across the top. So instances of, at runtime, what would you have? A player versus the player object or the player class. You'd have my inventory or an item, right, as opposed to specific. So a smackable, a breakable. Okay. So you're identifying that you have a specific instance of one of those objects. And that's kind of all you got to do for the next week. Now there's a methodology here where a lot of the assignments for this class have come earlier because in the back half of the term, all the assignments for the programming classes are going to come due. So I want to get these assignments done and out of the way. So try not to procrastinate on this. Just sketch it out, diagram it out, do a couple revisions. Again, I'm looking for the diagramming notation, not that you kind of figure out the magic puzzle, because I just grabbed a bunch of entities and a bunch of relationships and a bunch of actions from a bunch of different games that are unrelated.
And for the timing diagram,
yep.
Should you do all of those steps?
Yes. Or? Yes. Everything that's on those sheets, it's also in the assignment list, but every...
so the player has like 4 or 5 yet.
Yeah. All of these things should appear.
Okay.
Right? Everything appears once, at least.
Mm-hmm.
Right?
All the same diagram?
You can put them all on the same diagram.
We get to make up the process as long as everything gets used at least once.
Right. Right.
Okay, that makes total
right.
sense.
You get to define the flow. Right. There's kind of a flow. You can kind of work it out. Right. There's obviously some pieces missing. But again, you make up the flow. I'm interested in the way you draw it. The notation. Can you communicate it in the standard way? Okay?
Any week or 2 for this one?
You're going to make me go look? Oh, look. BFS Moodle logged me out.
Our next class with you will be in person, right? Or we have one on Friday if you don't mean. No.
Yeah, on Friday we'll do online.
Okay. And then Monday,
yeah.
Everybody goes back.
Bring your disease-ridden, nose-bloodied body in. Oh, look, I made this the end of the term. How silly of me. Oh well, that's what it's written down as. That's what it is.
Oh, so this is the last assignment for this.
Oh yeah, this is the last assignment for this class.
Oh, okay.
Oh, really?
Yep.
Yeah, but like you said, we're supposed to do this one early, not accumulate with the other class.
The
I have to get working on that second dice rolling game real quickly.
yeah.
Saturday.
If you haven't figured it out yet, usually if you have the same instructor for multiple classes, one of the classes will be programming heavy, the other one won't be.
We only have you twice. Wait, we have Derek twice actually.
Yeah.
So this one's not program heavy, but the other one is.
Right. Derek's one will be writing heavy.
Yeah.
And one of them isn't. Right?
Yeah.
Although he may make you stand up and speak in public.
Yeah, he's already done it to us already.
Yeah. Yep.
And lots of presentations. Like already 2 presentations.
I think the one is just all the design was going to be a lot of extra assignments. Pretty sure.
The
like 3 minutes.
Yeah, that one. Yeah, that's one.
Yeah.
I think is that one solo or team based? I think it's solo.
What are you worried about? We sit here and talk for hours.
Yes, but when it comes to me presenting my own ideas, I think my ideas are stupid, and I panic and don't know what to say.
I have only one thing to offer you. Get over it.
Yeah.